We lied to you. Okay? They're called guidelines here for a reason. All right? They allow us to predict whether or not a precipitate should form. How many of you remember in the lab where we had that little footnote that said silver sulfate is actually sparingly soluble? Yeah, even though we look up here on sulfates, where are sulfates? Right here. Compounds containing sulfate, except insoluble exceptions, are silver sulfate. Oops. Okay. There are exceptions to the rule. Things in chemistry, you should know this by now. You should expect this by now. In science, things are not necessarily always black and white. Things are usually right and wrong, but they're not usually black and white. We have to learn the rules. Okay? Now, the solubilities actually depend upon the magnitudes of, these guidelines depend upon the magnitudes of the water ion attractions in solution. What we started talking about at the very beginning of this semester. All right? And there is a quantitative aspect to this. Okay? Now, we just simply said things were soluble or insoluble. They precipitate or they don't. That's really, truly too simplistic of a picture. All right? Things are much more complicated. All right? A more complete view is that solubilities span a continuous spectrum between very insoluble and very soluble. And it's a continuous spectrum. All right? In other words, we can have really any quantitative value in between either end. All right? So, in order to explain these differences, we're going to use equilibrium. Because in fact, solubility, a dissolution reaction, an ionic compound dissolving in water, a dissolution reaction, is in fact an equilibrium reaction. All right? So, for example, we can make soluble compounds insoluble. Have any of you ever added enough table salt to water to see that the table salt starts to precipitate out of solution? I have. You're making a brine. You sit there and you add salt until you see salt no longer dissolve in solution. Okay? How many of you ever added sugar to water and seen sugar quit dissolving in water and you start getting a sludge of sugar at the bottom of your iced tea, for example? Okay? So you've made a soluble compound insoluble by adding so much of the compound that it's no longer soluble. There is a finite amount of the compound that can be suspended in solution. That's the wrong term. That can be dissolved in solution. There's a finite amount. It's not, nothing is infinitely soluble in water. Except water, but that's kind of an oxymoron. All right? Now, the exact opposite of that is also true. In the smallest amount, even insoluble compounds are in fact soluble in water. Okay, even something like silver bromide or lead chloride, something that we know pretty darn for sure is not soluble in water, there is a finite amount that dissolves. No ionic compound is 100% insoluble in water. Some of it gets into the water, period. It's one of the reasons why heavy metal poisoning is so important for us to avoid in environmental chemistry. Because once it gets into your body, it's going to stay in your body, even in small trace amounts. All right? So, solubility equilibrium. Here's an example, silver chloride. Silver chloride, we look at the list of the halides. All of the halides are soluble except for silver, mercury, and lead. Okay, that's what we learned from the tables back in chapter 9. I wrote an equilibrium for it. Why? Because silver chloride is sparingly soluble in water. Okay? Now, in order for us to define the solubility and to write a solubility equilibria, it must be an equilibrium in between the solid and its aqueous ions. Now, in order for us to have that equilibrium, we have to have a saturated solution. Saturated solution simply says there's an equilibrium between the dissolved ions and the undissolved solids. All right? In other words, in order for me to define a solubility equilibrium, I have to have some solid at the bottom of my beaker, bottom of my test tube, bottom of whatever I'm going to be using to hold my reaction. Okay? So, since it is an equilibrium, I already know how to write the big K for it. Just simply the concentration of everything that has a concentration that can change. In this case, The silver concentration can change, the chloride concentration can change, but the silver chloride solid concentration cannot change. Why? This is a heterogeneous equilibrium. We learned how to write these K's back in chapter what? 15? Yeah, 15. So this should not be new to you. All right, we just simply write the big K expression as the concentration of the species who have a concentration that can change. Those that are the aqueous. And we're going to define this since the value of X, whenever we solve for our ice table, since the value of X is called the molar solubility, and we're writing the product here of X twice or more, we're going to call this the solubility product. So these K's are called KSPs, but they're just a big K expression. I mean, we've had big KA, big KB, big KW, big KC, big KP, now big KSP. It's the same K. It's just specific to the solubility process. All right, now, show up for the in-class assignment and then leave. Thank you. Okay. So, these are going to be dealing with ionic compounds. All right. Ionic compounds dissolve in water to split up apart into their ions. All right. So, a general form for an ionic compound, we're going to have a metal and an anion together. We're going to have MXAY is the empirical formula for my ionic compound. It dissolves in water, and we get X moles of M, and M is going to have a charge of Y+. Okay, remember when I had you swap and drop the charges when we started writing the formulas for ionic compounds? Well, now instead of swapping and dropping, we're swapping and raising, okay, to get the charges on. Now, this is a general form. It's not necessarily always going to be true. You're going to know, you should know what the charge on the ions are by now. Okay, we've been hitting you over the head for that for what, at least 6 months now. Okay? And we're also going to get Y moles of the anion has a charge of X minus. All right. There's the general form of it, which means that my general KSP is going to look like this. The cation has a charge of Y+. That concentration is going to be raised to the X. The anion has a charge of X minus. Its concentration is going to be raised to the Y. Okay? Now, there is absolutely nothing new on this slide from what we learned back in chapter 15. Okay? It's just the way we write big K. All right? Now, some notes here. First of all, solids are not included in KSP. That's just because it's a heterogeneous equilibrium. That is absolutely nothing new. You've already been tested over that idea. You don't put solids in the big K expression. All right? We will always, always, always write the KSP as though the solid is the reactant. Regardless of how the reaction is going to be proceeding, we will always write the big K as though the solid is the reactant. Okay? That's important because we may be looking at this reaction going backwards. In other words, if I combine silver and chloride together in a solution, do I get a precipitate? But I always write it in this form. Solid is the reactant going to ions as my products. Pay attention to stoichiometry. It will eat your lunch. Okay? It's going to feel like you're applying the conditions of stoichiometry twice. When we start solving these problems, we're going to solve a lot of them. It's going to feel like you're applying stoichiometry twice. Right? Once when you write the KSP to get the exponent, and then again whenever you have to multiply by the stoichiometric coefficient times the concentration. All right? It's going to feel like you're applying it twice. You absolutely must pay attention to stoichiometry. I can absolutely guarantee you some of the wrong answers on KSP questions on the exam are going to be due to the fact that you did not apply stoichiometry correctly. All right? You can't do it. You're going to get the wrong answer for the wrong reason on the exam. All right? We think we come up with wrong answers. We don't pull them out of thin air. We randomly plug numbers in, just like you do. Hopefully not. Hopefully you don't. Okay. Some terms for you. Molar solubility. It's the moles of solute, the undissociated solute, in 1 liter of a saturated solution. Okay? Now, it's not the solute. The solute are the ions, but we've defined the molar solubility as the moles of the reactant which dissolve in solution. meaning we report the solubility in terms of 1 mole of sodium chloride, or 1 mole of barium chloride, etc. All right? It's always going to be in terms of the reactant. And you're going to have to apply stoichiometry to know what the concentrations of the ions are in solution. Okay, solubility. We either do molar solubility or solubility. Solubility is the grams of solute. Again, that is grams of the solid reactant, which dissolve in a saturated solution. This can either be grams per liter, or this can be grams per 100 milliliter, or gram per whatever it's listed as. Okay? Now, we can use KSP to determine either solubility or molar solubility. It's an equilibrium problem. Meaning you're going to use an ice table. Remember I told you when we introduced ice tables, we're going to use them for the next, what, 3 chapters? We're still using them. All right. Actually, this will be the last topic on ice tables. It won't be the last time you see Big K, but it'll be the last time you do ice tables, specifically to solve a problem. Okay, now, larger KSPs, meaning that the equilibrium is favors the products. Larger KSPs are going to lead to a larger solubility. And of course, we can use molar solubility to compute K, because molar solubility is in terms of basically its molarity, mole per liter, so it's a concentration term. All right? So we can use it to calculate KSP, and we just simply plug in the molar solubility into the KSP expression, multiply, and raise things to powers, and we're done. All right? So there's nothing really new here, it's just new applications, and the math is going to look a little bit different because, well, it is different. All right? We don't have to deal with fractions anymore. All right, so silver bromide. It is a halogen. It's silver, mercury, or lead, and a halogen. Therefore, we would predict that it is insoluble. Question is, determine the KSP of silver bromide. If 8.87 moles can be dissolved in 1 liter of an aqueous solution. Okay? So, first things first, I need to write the dissociation equation. I need to write the chemical equation that governs everything that takes place. All right, by the way, this is exactly what we did the very first day in class, right in this room when we talked about the syllabus, and I started asking what's in solution. Why? Because we were going to be dealing with what's in solution all semester long. Okay, so I have silver bromide, solid. Dissociation reaction or dissolution reaction, either one is appropriate here. It's going to dissolve in water. I don't necessarily need to write the water on top of the reaction arrow. It's going to split apart into its ions. And I get silver and bromide. This is what's going on in my beaker. This is the chemistry. The rest is math. Okay, write the KSP expression. Well, this is a solid. Its concentration never changes. Aqueous, those concentrations change. So KSP is going to be the silver concentration times the bromide concentration. Now I'm going to divide by silver bromide because its concentration doesn't change. Set up an ice table. Okay. Now, this concentration does not change. All right? But some of this does dissolve. All right? And in terms of the definition of molar solubility, I really need to know how much of this goes into solution. All right? But this doesn't change. All right? My initial quantities, my initial amount here is 0 and 0. I really don't care what the initial amount is here. It doesn't matter. What does matter is how this thing goes to equilibrium. All right, now, whatever dissolves into solution, I know that 1 mole of this dissolves, giving me 1 mole of this and 1 mole of this, meaning these need to have the same stoichiometric coefficients. So this is going to be minus x plus x plus x. At equilibrium, this value hasn't changed from its initial value. The only reason why I write a C value here, or a change value on my ice table, is to make sure that, explicitly ensure that my stoichiometry is correct. 1 mole of this dissolves to give me 1 mole of that and 1 mole of that, meaning all of these have to have 1s in front of whatever the change amount is. Okay, so at equilibrium, this is going to be X, this is going to be X. Okay, now, it says to determine KSP of silver bromide if 8.87 moles can be dissolved in 1 liter of aqueous solution. Okay, that 8.87 moles in 1 liter tells me the concentration, basically it tells me the value of X. Okay, tells me how much went into solution. All right, now according to my ICE table, KSP is equal to silver bromide times silver concentration times bromide, which is going to be equal to X squared. And the problem tells me what X squared is, or tells me what X is. So KSP is going to be equal to 8.8 times 10 to the minus 7 moles in 1 liter, so that means this is technically molarity, times 8.8 times 10 to the minus 7 molarity, but K's are always unitless quantities. So, this comes out to be 9.38 times 10 to the minus 4, and this is equal to my KSP. In this case, I got it because I was told how much dissolves into solution. Okay? Now, the way the problem is stated, it says this, somebody getting a different number? Anybody else getting a different number?
7.
What do you get?
It's 7.7 times 10 to the negative 13. I may have put it in wrong.
No, somebody else said it's right. The number didn't look right to me. It should not be times 10 to the minus 4. I don't know what I did. I solved it wrong. You got what, 7 point what?
7 times 10 to the negative 13.
That actually sounds better. Okay. Now, let's go ahead and do another problem based upon this. All right, in this case, it told me how much silver bromide dissolves. It told me this number. All right, in terms of moles in liters. Now, let's convert this. That's the molar solubility. How much of this actually dissolves in 1 liter? Okay, so I have 8.8 times 10 to the minus 7 moles of silver bromide in 1 liter of solution. So that means 8.8 times 10 to the minus 7 moles of silver bromide can go into 1 liter of solution. How many grams will dissolve in 1 liter of solution? Anybody know what the atomic mass of silver bromide is? Should be big. No, silver's 107 point something. What do we get? $187.8. Go ahead and multiply that times 8.8 times 10 to the minus 7. What do you get?
1.6 times 10 to the negative 4.
That's
1.7, I'm sorry.
1.7 times 10 to the minus 4 grams of silver bromide will dissolve in 1 liter. Okay, that's 0.17 milligrams. not even an entire crystal of silver bromide will dissolve in it takes an entire liter to basically dissolve one crystal of silver bromide. Yeah, it's not very soluble. But in fact, some of it does dissolve. Okay? Some of it does in fact dissolve, even though it's classified as an insoluble compound. Okay. Molar solubility of silver chromate is 6.7 times 10 to the minus 5 and 25. What is the solubility product of silver chromate at 25 degrees C? Now, all of these solubilities technically need to be reported at 25 degrees C. Or, if the temperature is not specified, you need to assume it's 25 degrees C. If it's another temperature, well, we won't know until after exam 3 how to do that problem. All right? So, first step is to still write down the solubility equilibrium. So silver chromate, Ag2Cr04. This dissolves in water. What do I get? Now remember the list of polyatomic ions I told you to memorize, and you had flashcards and you memorized them for the next exam and you haven't looked at them since? When's the last time somebody saw chromate? Last semester? Yeah. Well, what happens if you don't remember that silver is +1? Then you've got to know what chromate is. Okay? You know it's a 2-to-1 ratio stoichiometrically, but what about charges? You've got to make sure you know those polyatomic ions. Okay, so write my dissolution reaction. Go ahead and write my KSP expression. KSP is going to be the concentration of silver squared times the concentration of chromate. Set up my ice table. First row here doesn't matter. This is a 0, this is a 0. And go ahead and write down the first row, because what do you think the first thing that's going to affect solubility is going to be? Common ion effect. All right. So, this is a 1 to 2 to 1 reaction. So my change here is going to be minus x, even though technically it's not changing. Follow how I'm setting this up conceptually. Meaning I'm going to get how many moles of silver? If x is 1, how many moles of silver do I get? 2. This is going to be plus 2x, plus x, 2x, x. These are my equilibrium values. I can plug those into the KSP expression. Okay, this is where it feels like you're applying stoichiometry twice. I've got stoichiometry here because of the exponent. But guess what? I've got stoichiometry here too because it's 2x. This is going to be 2x quantity squared times x. If you forget the quantity, you missed the problem. Okay? All I did was I took this number here, plugged it in for the concentration here, and then it gets squared. Okay? The 2x for the concentration, this is the concentration of silver, it's 2x. I'm looking for x, or in this case I'm given x, but I need KSP. I'm given x, I'm not given 2x. I'm given x. So I'm going to plug 2x in for the concentration of silver at equilibrium. But the concentration of silver gets squared. The 2x gets plugged in for silver, but silver is squared, meaning I have to put a quantity squared here. I know I've said that 3 times. There's a reason why. You're going to screw it up. All right? So I go ahead and multiply this out. 2 squared is 4. X squared is x squared times x is cubed. Okay, now the way the problem states here is it tells me the molar solubility. It told me the molar solubility of silver chromate is 6.7 times 10 to the minus 5. What's the solubility product? It's asking me to calculate KSP. Okay, so KSP is going to be equal to 4 times X, which is the molar solubility. 4 times 6.7 raised to the minus 5 power, I'm sorry, minus 5 to the 3rd power. You should have a YDX key on your calculator. This is where it comes in handy. Now, if I did this one right, I think I did. 1.1 times 10 to the minus 12. Okay? You cannot determine solubility solely by looking at KSP. You also have to take into consideration stoichiometry. All right? It does make a difference. All right. So these are both of these problems involve me giving you the molar solubility and you plugging that into the KSP. There was no solving for X because I gave you X. By the way, I think, and I'm not positive, that your textbook all of a sudden switches from using X to S in the ICE table. Anybody confirm that? Yes, no? Anybody haven't actually looked at the textbook yet? No? Okay. If they use S in the ICE table, it's solely because S means solubility. I think it's stupid to change it at this point in time. I'm going to do everything in terms of X because that's what you've been seeing all semester long. All right? Just warn you, it may not do that. I don't remember. I didn't know this one. Okay, another problem. What's the molar? Uh-oh. Now we're going the other way. What is the molar solubility of lead iodide? That would be lead 2 iodide. And I give you the KSP. Do it. ICE table. Solve it. Find a friend. Phone a friend. We'll hold the audience here in a minute. By the way, the first step is the same as what we've been doing. Second step is the same as what we've been doing. The third step is the same as what we've been doing. The fourth step is different. We're not plugging in for X, we're solving for X. I don't hear enough talking going on. You talk more when I'm lecturing than you are when you're solving a problem. There's a problem with that. The dull roar while solving problems is a good thing. Dull roar during lecture is wrong.
Well, at least we're catching up to the lab.
Yeah. See, but this would help me when I was doing the lab thing.
Yeah.
But now I was really yeah, it was awesome.
Okay, who's done? Who's not done? Okay. So, how do we work this problem out? Same scenario, the only difference is the very last step. First step, always write down what's going on. Write down the dissolution reaction of the ionic compound that you're interested in. All right? Go ahead and fill out your ICE table if it's necessary. It has been necessary for every problem you solved so far. Write down your KSP expression. In this case, KSP has a numeric value, meaning I'm solving for x. All right? So, write down the numeric value. Go ahead and plug in the equilibrium values. X and 2x. X and 2x. Again, it's going to feel like you're applying stoichiometry twice. Once to get the squared here, and then once to get the 2x in front of the 2 in front of the x here. It should. If it doesn't, you did something wrong. That's probably the number one mistake you guys are going to make. All right? Plug that in. 2 squared is 4, x squared is x squared times x, 4x cubed. 4x cubed is equal to KSP, and then you just simply solve for it. Okay? You may or may not have a cube root key on your calculator. I suggest you pull out your calculators and find it. Okay? If all else fails, you can always do the y to the x key, and the x in this case is 1/3. All right? Okay. Not horrible. No, it's not. It gets a little bit more difficult. Okay. Calculate the solubility in grams per liter at 25 degrees C for SN. What is SN? 10. So that would be what? 10(2), 10(4)? Stanic sulfide. Okay. So work it out.
Yep.
And these things are not horrible. Compared to a buffer problem or a titration problem, this is a piece of cake.
Like by the grams, like to change it from moles to
Yeah.
grams, right?
Yeah. I know sulfur is 30.7. Or no, 32.7.
Plus?
118.7. Oh, sorry. It's 32.07. Sorry. 150.
Okay.
77.
Problem is identical to what we've already solved until the very end. All right, remember that big K's are always in terms of molar concentration. All right, so when I solve the ICE table, I get molarity. But the problem doesn't ask for molarity. The problem asks for grams per liter. Molarity is moles per liter, so I must convert my molarity to grams per liter. All I do is multiply by the molar mass of whatever it is that's dissolving in the solution. All right. I have a KSP over here of 1 times 10 to the minus 26. Yikes. Solve for x. Multiply times the molar mass. 1.5 times 10 to the minus 11 grams. Okay, we're talking what? Milligrams is 10 to the minus 3rd. Micro is 10 to the minus 6. What's that for micro? Nano is -9. -12 is pico. We're talking about 15 picograms will dissolve in 1 liter of water. All right. Now, that's measurable in some techniques. Not anything you're encountering in a Gen Chem lab. All right. But that could be enough, depending upon exactly how tin messes with the body. All right. Sulfide's not going to necessarily do anything in the body, but tin might. I mean, how much tin are you consuming if you actually drink out of one of the old-timey tin cans? How much aluminum are you consuming when you drink out of an aluminum can? Answer there is none, because they put a protective coating in there, because the phosphoric acid in soda or the carbonic acid in beer would dissolve the aluminum can. So they put a plastic lining in there. In fact, you can open up a can, take a nail and scratch that plastic lining off, let it sit overnight, and you can just rip the can in two. All right. Let me see. Okay, so there are some factors that affect solubility in addition to temperature. We'll talk about temperature effects after the exam. There is a common ion effect. pH. If I have something in solution that ionizes water, or if, for example, I have an insoluble hydroxide, I can affect the solubility by tweaking the pH. Also, complex ions can form. All right. Complex ions are, well, they're complex ions, which are soluble as one big massive thing in water. All right. And in chapter 14, actually this should technically be chapter 15.4, solubility, the temperature can affect the solubility. Okay, so the common ion effect, we already know what it is. It's a quantitative application of ladies. I'm sure you're not talking that much about chemistry. Thank you. All right, common ion effect, again, it's just nothing more than the quantitative Le Chatelier's principle. All right, so if we look at something like calcium carbonate, all right, carbonates are typically insoluble in water. Calcium carbonate is sparingly soluble in water. Dissolves to give me calcium plus carbonate. Now what happens if I add something like calcium chloride to that solution? Okay, calcium chloride is a chloride, so that means it is soluble in solution. It's going to separate into its ions. I'm going to be calcium and chloride. I'm adding calcium. I'm adding a reactant here. So what's going to happen? It's going to cause the precipitation of calcium carbonate. Again, Le Chatelier's principle. All right. Last semester you would have seen that, and you would have, told me there was a precipitation reaction. All right. So the equilibrium was going to shift left. Common ion calcium lowers the solubility of calcium carbonate. Meaning the solubility of calcium carbonate in a solution of calcium chloride is lower than the solubility of calcium carbonate in pure water because of the common ion effect. All right, so what is the molar solubility of lead iodide in a 0.1 molar sodium iodide solution where the KSP of lead iodide is 1.4 times 10 to the minus 8? All right. First things first. Write down the chemical equation of what's going on. Okay? Now, the initial concentration of lead iodide does not matter. The initial concentration of the lead, I'm going to assume is equal to 0 because I'm asking myself what is the molar solubility of lead iodide. I want to know how much lead iodide gets in the solution, which means hopefully I'm assuming that there is no lead in solution to begin with. However, I have a 0.1 molar sodium iodide solution. Okay, that's 0.1 moles per liter of sodium, 0.1 moles per liter of iodide. What does sodium do in solution? Nothing. At this point, hopefully all of you say nothing. Sodium never does anything. It's boring. But the iodide, I'm going to start with a 0.1 molar solution. That's by common ion. All right? Now, just like what I did whenever I looked at the common ion effect of sodium acetate in acetic acid, I'm going to let this re-equilibrate. Minus x plus 2x. Stoichiometry is a bear in this with this stuff. At equilibrium, I do not care about the lead iodide. Lead is going to be x. Iodide now is going to be 0.1 plus 2x. All right, so write out my KSP expression, write down my value of KSP, and solve the problem. All right, so KSP is going to be the concentration of lead times the concentration of iodide squared. That is equal to 1.4 times 10 to the minus 8. Plug in my equilibrium values. Lead is x. Iodide is 0.1 plus 2x quantity squared. Oh, great. 1.4 times 10 to the minus 8. We thought we got away from the quadratic and other nasty beasties of a calculation, didn't we? No, we did not. And in fact, the worst case scenario I can think of is a fifth order polynomial here. Now, if there is a fifth order polynomial, I guarantee you're going to solve it with the extra small approximation. Okay? Now, let's look at this. Okay? The solubility of lead iodide by itself is 1.4 times, well, we did the molar solubility of lead iodide well earlier, didn't we? That's 1.5 times 10 to the minus 3rd molar. Okay? Now, if we stick a 0.1 molar solution of sodium iodide in there, what is this going to do? It's going to shift this thing back this direction. But K is already fairly small, right? Meaning this is not going to go far, this is not going to go very far forward. Meaning compared to 0.1, even 2x is an exceedingly small number. Okay? So what I'm going to do is I'm going to use the x is small approximation. Okay? I'm saying that this value of x, actually this value of 2x is smaller, is significantly smaller than 0.1 here. Okay? So I'm again going to have two different colors of x, a black x and a red x. All right? So I'm going to solve for the black x. Where the x downstairs is going to be treated differently. Okay? Now, for my first x is small approximation, I'm going to assume the red x is equal to 0. Meaning my black x is going to have the following value. Okay? 1.4 divided by 0.1 squared, which 0.1 plus 2 times 0, so it's 0.1 squared. 0.1 squared is 0.01, so I'm dividing that by 0.01, meaning x is going to be equal to 1.4 times 10 to the minus 6. Okay? So I am now going to plug that number in for my red x. So this is going to be x0, x1, 1.4 times 10 to the minus 6. Plug that in for the red x, times 2, plus 0.1, square it, divide that number by that. And my next x is going to be, if I remember correctly, well, I've got the number wrong, I'm going to try to remember. This is fun. This is 1.4 with a bunch of zeros after it. Why? Because I only know the KSP to 2 digits. Okay, so this is 1.4000000 because I don't know anything other than that. This becomes, this is kind of neat, 1.39999999, I can write 9s all day long, times 10 to the minus 6. It changes by 0.01 times 10 to the minus 8. It's converged. Okay? meaning that my molar solubility of lead iodide in 0.1 molar sodium iodide, my X is going to be 1.4 times 10 to the minus 6 moles per liter. All right. If you compare that to what we calculated 2 slides ago, or on page 4, on slide 44, the solubility of lead iodide in water was 1.5 times 10 to the minus 3rd. Okay? The common ion effect changed the solubility by 3 orders of magnitude, a factor of 1,000. All right? And that is one of the ways that we can cause selective precipitation and get rid of some of those heavy metals in water so that it becomes safer to drink. All right? So, thank you for your time and your attention. We will finish up this chapter finally on Monday.